Okay.
Okay, so good afternoon and welcome to the last talk for this semester of the World of EE. Today we are delighted to have Dr. Eran Socher from the Department of Physical Electronics. So Eran got all his degrees in the Technion, bachelor's in physics and electrical engineering, and then master's and PhD in electrical engineering. And then he spent 2 years in UCLA. And since 2008, right?
Mm-hmm.
Since 2008, he's a senior lecturer here in the Department of Physical Electronics. And today we'll hear about, I guess this is RFICs, but in a more friendly...
In a way, yes.
Yeah. Okay, so please.
Okay, so good afternoon, everyone. My name is Eran, and as Adi mentioned, I'm a faculty member here in the School of Electrical Engineering, Department of Physical Electronics. The research side of what I do is RFICs, radio frequency integrated circuits, which is really related to what we're going to talk about today. And on the teaching side, I teach analog circuits for undergrads. Next semester also a more advanced course on analog circuits, and RFIC circuits, which is for graduate students. And what I wanted... RFICs is radio frequency integrated circuits. Okay. So today what I wanted to talk to you about is perhaps give you some perspective on communication circuits, where they come from, or the basic concept behind these circuits, and what is the role of miniaturization in making these concepts and circuits applicable for modern life as we know it in mobile devices, like all the mobile devices that you carry in your pocket, in your laptop, in all those devices that really transform our lives in the past years. So first, as I mentioned, I'm going to talk briefly about the concept of radio communication. What is the basic principle of operation of such systems? I will give some historical examples of radios as they used to be in terms of the system, the devices that were being used. And then we're going to talk a bit about what is the challenge of taking these communication concepts and systems and put them into a device like this, okay? And which brings us to the question of scaling. How do those things scale if you want to make them much smaller? I will give some examples of mobile integrated circuits that are being used in such systems. And I'm also going to give you some examples on the research that we're doing currently at the university for future integrated circuits for future applications of communication, which means how this field might look like in a few years, what kind of chips and applications would be then. Okay. So first of all, about the concept of communication. Well, you can define communication in many ways, but as the way that communication started to be more significant, it really involved the communication of voice, right? I mean, you can talk about Morse codes and something very fundamental like that, but it started transforming people's life when you were able to communicate voice, okay, like telephone and radio and things like that. And if we consider what kind of signals we're trying to transmit, then the human voice has acoustic waves, is carried by acoustic waves, frequency range typically between 20 hertz and 20 kilohertz. This is the spectrum. This is what we're trying to transmit. So if you want to communicate, and you can talk, and if you want to communicate between two different people, then why not just shout, right? I mean, what's the problem? Why are we talking about electromagnetic radio waves? Radio waves are much higher frequencies. So if this is the frequency, why not just do it? What do you think? Why don't we just shout away, and that would solve our problem of yeah, I mean, we do, but what's the problem? What do you think? Why do we need radios? Why don't we just shout? What are the two main problems?
The distance.
Okay, the distance. Okay, so of course, acoustic waves, if we just want to transmit them, they cannot be transmitted wirelessly for long distances, right? It decays, and that's it. I mean, you cannot shout for a distance of kilometers. I mean, I don't know anyone who can. But electromagnetic waves can, right? I mean, there is much better transmission of electromagnetic waves at those frequencies that can travel kilometers, tens of kilometers, hundreds of kilometers, even across the oceans, depending on the frequency that is being used. And this is, of course, a much more effective way of transmitting information over long distances. So this is why these waves are being used. But also, there is also the question of how many people can talk at the same time. If we're all using voice, right, so I can talk and another person is talking and another person is talking, we're all using the same frequencies, the same frequency range of 20 hertz to 20 kilohertz. So it means that all those things overlap. So we can't all talk together, okay? Even if we use electromagnetic waves, we cannot all use the same frequency because they would overlap and we cannot really talk together. So the fact that we're using much higher frequencies, like radio frequencies, allows us to use portions of frequencies that are, let's say, 20 kilohertz of bandwidth, one next to the other, so that a lot of people can talk together because they use slightly different frequencies. So if we take the acoustic frequencies, convert them into electromagnetic waves at a different frequency, everyone having its own specific frequency, we can share the spectrum, and many more people can talk at the same time and communicate at the same time, which is, of course, a very big advantage. So in order to facilitate that, we need to understand one very basic concept, which is upconversion and downconversion of frequency. So if, for example, we take a look at the voice spectrum, which is typically at a very low frequency, as we said, kilohertz. So this is like a frequency view of that signal, right? I mean, the amplitude or the signal that we have as a function of frequency. So it's all centered here around the low frequencies. And we want to transmit something in radio waves. When we talk about radio waves, what kind of frequencies we're talking about then? Any ideas? Well, it's a very wide spectrum, but let's say when you use your FM radio, what kind of frequency you're talking about? Something like 100 megahertz. Of course, much higher frequency than the frequency that we use for voice. If we talk about your cell phones, what kind of frequencies the cell phone use? 1 gigahertz, 2 gigahertz. Wi-Fi that you're using? Well, there are several bands. Maybe 2.4 gigahertz, 5 gigahertz. This is more or less the range of frequencies that we're talking about usually when we talk about RF. So it means that you take a signal, which is kilohertz, and you want to convert it to gigahertz range, maybe. How do you do that? You multiply, use something that is called a mixer. So you take a carrier wave, that can be 100 megahertz or 1 gigahertz, and you multiply it with the signal that you have for the voice. And what is the result? If you multiply two signals at two different frequencies, you get the sum or the subtraction or the difference between those two frequencies, which means that what happens is that this spectrum that you have here of the voice, let's say, is now being upconverted around the carrier frequency of your choosing, let's say 1 gigahertz. So now you have this spectrum of 20 kilohertz or so around 1 gigahertz. And this is now being transmitted through the atmosphere. So what happens at the other side, at the receiver? So once you have this signal being transmitted, it now needs to be downconverted, okay, to be understood what is the information that is being transmitted. So a similar process is happening, where this signal is now being multiplied also with a local oscillator on the receiver side, where the output is going to be the difference between those two frequencies. So when you take this, you multiply it with the carrier wave, let's say, again, at 1 gigahertz. So actually you get a difference of the frequencies, which is what you're looking for, because this is the original spectrum. And you also get a sum of those frequencies around a much higher frequency that you don't really care about, and you filter it out. Okay, so you select only the low frequencies of interest, the original data that you wanted to transmit. So you take low frequency, you upconvert it, transmit it, then on the receiver side, you downconvert it and retrieve back your information. Okay? Okay. And of course, if you want many people talking at the same time, then each of them is going to use a slightly different frequency. So you're able to select the right user. So if you want to see how a typical communication system looks like, then you have an information source. It can be voice. It can be something else. It can be, you know, a video data, some digital data that takes up some bandwidth of information, which is typically much wider than voice. Okay? Then you modulate it around the carrier, as we discussed. You transmit it. Then it goes through some channel. It can be free space. It can be optical fiber. It can be all cable, all kinds of channels that can transmit information. And then it arrives at the receivers. At the receiver, typically it's being amplified first, and then it's going to be demodulated, downconverted back to low frequency, and arrives at the information sink, the client that really wants this information. So it can be you listening to what someone else is talking about. It can be some video screen showing the video that you just transmitted, or any other client. Okay. Another view of the same concept, we have our data stream, again, coming from all kinds of sources, video, audio, or whatever, files of some kind, modulation, power amplification, usually, because before you transmit it through the atmosphere, it has to be amplified to have enough power so that it would survive the way. Then it's going to the air through an antenna. This is like a symbol of an antenna. And once again, on the receiver side, first picked up by an antenna, amplified, because the signals are usually pretty low coming from the antenna. Then the mixer, demodulating, using a local oscillator, or what is depicted here as a VCO, voltage-controlled oscillator. You want to control the frequency that you're using. Filtering, again, amplification, and then maybe an A to D, sampling this information from the analog world. A to D is analog to digital. You take the analog information that you have here, convert it into digital data. Okay? Let's say we want to have everything digitized nowadays. So your video is going to be digital data. Your voice is going to be digital data. Files that you're sending are digital data. So it's all being sampled and digitized. The basic concept that we're talking about here of upconverting, downconverting, using electromagnetic waves dates 100 years and more back. Okay, some of the classic architectures that people use even nowadays for communication were conceived by Edwin Armstrong maybe 100 years ago. A lot of the concepts that are still being in use today are really quite old, the basic concept. Okay? And we can show some historical examples, right? I mean, how those things looked when these things started. Some classic radio sets that you can see are as big as a person, okay? Devices that are being used. Does anyone recognize what are those things here? Okay, but the device itself, I mean, it's maybe being used as amplifiers, but the active device is based on vacuum tubes, okay? Bulky devices that are being used to amplify either the radio signals or the audio signals also use these kinds of active devices. Another example of a radio set. And you can see that these devices are pretty big, heavy, take a lot of space, probably cost a lot of money also. Okay? And other things that are being used in this world of radio that probably you're familiar with your everyday life are antennas. I mean, you don't really see the antennas here, but antennas that are being used just so that you get familiar with the concept. Does anyone know what kind of antenna is this? Yagi, yeah. This is a Yagi antenna or Yagi Uda antenna. And when you look at aerials, you know, on top of buildings and things like that, you see a lot of variations on this concept. Okay? What about this one? What kind of an antenna is that? Loop antenna, right? And this is an outside version. Many of you, if you have some antennas for radio inside your house, also many of them also use loop antennas. I don't know if you noticed or not, but these are classic structures for antennas. These are typically to receive, but also to transmit radio waves. And as you can see in these examples, these can be pretty big. Other devices that are being used that take a lot of the space that you see here in these classic radios are passive devices. I mean, in addition to the active devices that actually amplify signals, like the vacuum tubes here, are in radio circuits. We need a lot of passive devices to select the right frequency, for example, using resonance between an inductor and a capacitor. So how do we make such devices? Classically, what you see here are inductors. What is an inductor? It's like a coil. What happens when you have this kind of coil structure of a metal wire? Because you have current going in those loops of the coil, you have magnetic field inside. Because of the change in time or the fact that you have a frequency, a current that has a certain frequency, then you have a change in the magnetic field, and this is translated as an inductor. That you have this kind of relationship between the current in the device and the voltage in the device. So in order to have these kinds of coils, it takes some space. And does anyone know what this is? This is a capacitor, not just a regular capacitor, but a capacitor that you can change its capacitance, right? When you have a capacitor, you have an electrical field between two metal plates. If you want to change the capacitance, you need to change the area, right, that they overlap. And this is how this thing works. You can rotate it, and then you have a different area of overlap between the two metal plates. So it's a variable capacitor. Why would you need a variable capacitor in a radio? Let's say you want to tune the frequency. You want to change the frequency of resonance. You have, let's say, one inductor another capacitor. If you change the capacitance, you change the resonance frequency, you change the station that you're listening to, the frequency that you're now receiving. So if we have all these kind of bulky devices, so how would that fit into a mobile device, right? I mean, what are the problems? What are we going to do with the antenna? If the antenna is very big, how would that fit into a mobile device? You're not going to carry like this pole around everywhere. I mean, some soldiers do, but probably it's not a very wise choice. Okay. Now there is the radio frequency circuit itself. It takes a lot of space. It's very big, potentially, and also a lot of power. I mean, if you need to operate all those active devices and they consume a lot of power, then it's kind of a problem consuming all this power in a mobile device. So it also relates to the battery issue. If you consume a lot of power and it all needs to come from a battery, then of course you have a problem. And of course, if you want to have a mobile device like this that is not just doing communication, but is doing a lot of digital processing, okay, because you want to process all the information that you're transmitting and receiving, so this also means that it takes a lot of space and it consumes a lot of power. So again, how do you fit all those things into a mobile device? And of course, if you need all those devices and many active devices, many passive devices, it all comes to a question of costs. So maybe you can make something like this, but it would cost you $1 million or $10 million, so no one is going to buy it. So it's not practical, right? So how can something like this be possible? So part of the answer is scaling, okay? So things can change their size depending on different parameters, such as frequency, right? So if we talk about the antenna size, what determines the antenna size? Well, I'm not going to go too deep into electromagnetism, but antenna elements are typically of the with the size, the order of the radiation wavelength. And what is the radiation wavelength? Let's see some examples. If we talk about 100 megahertz, as we said, FM radio, then the wavelength is 3 meters, which means that a typical antenna size need to be meter size. If we talk about cell phones, then typical frequency is 1 gigahertz, and the wavelength of the radiation, the wavelength is inversely proportional to the frequency. It translates into 30 centimeters. Smaller than this, but does it really fit in here? Maybe if you fold it enough, okay? And if we talk about higher frequencies, I'm going to talk about some examples in that frequency range. If your frequency is maybe 100 times higher, you're using frequency of 100 gigahertz, perhaps in the future, for future communication applications, then the wavelength is going to be 3 millimeters, much smaller. Okay? What about the passive devices that we're using? As I mentioned before, you know, the passive devices can take a lot of the space in your RF circuit in most of the cases. And the size of those devices also depend on the frequency that you're using. Okay? How so? What are we trying to do with those passive devices? One of the functions that those passive devices are doing is impedance transformation. So we care about what is the impedance of the passive device that we're using. Let's say it's an inductor. If we talk about an inductor, what is the impedance of the inductor? Does anyone know? It's already written here somewhere. So it's actually omega L. Omega is 2 pi f, the frequency that you're using, and L is the inductance of the inductor. So let's say that it should fit into some typical impedance that is being used in radio frequencies, and And one of the most characteristic impedance that people are using is 50 ohm. I don't know if you ever connected any coaxial cables or things like that. Then many of them are 50 ohm or maybe 75 ohm, but always in this range. So if, for example, we want this omega L to equal 50 ohm, it means that for different frequencies, we're going to need different orders of magnitude of devices. So again, 100 megahertz FM radio, 80 nanohenry translates into 50 ohms. If you're talking about cell phones, 1 gigahertz, then it's 8 nanohenry. If you're talking about 100 gigahertz, then the typical inductor is going to be 80 picohenry. Okay? Much, much smaller. How does this translate into size? What determines the size of the inductor that I need? If I need an inductor with 80 nanohenry or 80 picohenry, what is the size that is required? If I want an inductor that has more inductance, what do I need to do in those pictures here? I want more inductance. What do I need to do? I have two options. One of them is to increase the number of turns in the coil. If I have more turns, I have more inductance. And another thing that I can do is increase the area where you have the magnetic flux. Okay? So both those things increase the inductance. So in many cases, there is a limit to how many turns I can actually make. So let's take some typical number of turns. If I want to increase the inductance, I need more area. So the area is related to the inductance that I need. So if I need more inductance, I would require more area, a bigger inductor. Okay? So if I go back to what we're doing here, then typical numbers might be that if I need this kind of inductance of 80 nanohenry, then perhaps I need several millimeters for the inductor, at least. If I'm in the gigahertz range, maybe less than a millimeter. If I need 100 gigahertz, then I need much, much smaller inductors that can be in the micrometer range, something that can fit inside an integrated circuit. Okay. Yes?
What changed? The theory was known 100 years ago. What changed that allowed people to build smaller devices? Why people 100 years ago didn't build this tiny radio and use this bulky radio?
Okay, so a few things didn't really exist 100 years ago or tens of years ago. If we're talking about the active devices, then the active devices that existed 100 years ago were big. Okay, so if you wanted to create something that a circuit that is much smaller, you couldn't do it because your devices were too big. Also, if you wanted to create passive devices that are much smaller, you also had a problem. Let's say you wanted to create something that is micron size, you couldn't machine it. You couldn't create something that would be so small. In addition, it's not just about the single element device. I mean, maybe you can create one device that is very small, but you don't need one device. You need maybe 1,000 devices, 1,000,000 devices. How are you going to connect all of them together? Okay? So you need to be able to miniaturize your devices, and you need a way of connecting all those devices together. And this is what really transforms this world, is the fact that nowadays we have integrated circuits. Circuits that are being implemented on semiconductor substrates in parallel that integrate many, many, many millions of active devices and passive devices. If we didn't have this kind of capability, we couldn't integrate those circuits. And it really was not possible 100 years ago or 50 years ago. So, for example, if we talk about these inductors that are being integrated inside an integrated circuit, so how does that look like? So the typical integrated circuit looks something like this. Okay, typically it's made of silicon, and this is kind of a cross section of the process. You have a substrate. The thickness of the substrate is maybe a few hundred microns, and then you have some thin layers above it. This is an insulating layer, silicon dioxide. It's kind of a glass. It's isolating the silicon substrate from the layers that are being implemented on top. And this is a metal layer. And in this metal layer, that can be made of aluminum or copper. The thickness is something of the order of a micron, maybe less. And you can pattern a two-dimensional structure, let's say this kind of spiral inductor. So what we have here, as you can see here we have a loop, another loop, and then I use a different metal layer to go underneath the loops outside. So this would be a two-loop inductor. Okay? And when it's being implemented, it's not exactly the same device, so it's going to look something like this. This is kind of a top view of a chip. So this is going to be the inductor. Here it's a three-loop inductor. And in this case, it's just the inductor connected to metal pads that allow us to connect to it and just test this single element. And on the same substrate, on the same silicon substrate, we can implement many of those inductors, which can be, tens of microns, even millimeter size. And on this substrate, we implement also a lot of transistors, a lot of active devices that can be used for amplification, signal processing, and all those other functions. And if you ask what is the difference between what was a few years ago and now, again, it comes to scaling. And when people talk about the integrated circuit scaling trend, they use, in many cases, what is known as Moore's law. Have you heard about Moore's law? So there are different variations of this law. This is one representation of this law, which means that the integration capability grows exponentially with time. Okay, so I look at what we have here. This is the year. And here, this is the number of transistors in a chip, in a digital processor. In this case, it's Intel processors. So you can see the exponential growth in the number of transistors that you can integrate inside a chip. So it starts with something of the order of 1,000 when you talk about 1970. And nowadays, it's in the range of billions. Okay, so a typical digital processor that you have in your laptop or your desktop or your mobile device has something in the order of 1 billion transistors. Okay? Another manifestation of this scaling trend, this is possible because transistors are being smaller, so you can integrate more and more and more of them together on the same chip. Another manifestation of this scaling is actually also the transistor speed. How fast can it amplify? So you can see here also the growth of the speed of the transistors when you go from one technology node to the next. Transistors are being made smaller, and as a result, they're also being made faster, which means that technologies that can operate at low frequencies before can amplify signals at higher and higher frequencies nowadays.
What is the difference between FT and Max?
Okay, so this is for a more advanced crowd. FT is the cutoff frequency of the transistor as a current amplifier. Fmax is the cutoff frequency of the transistor as a power amplifier. So there is a slight difference in that. But it's on the same order of magnitude. What is the motivation of scaling? Why do people do scaling? Why does Intel want to fabricate nowadays at 22 nanometer and then in 14 nanometer technology and less and less and less? If we have smaller transistors, we have more transistor on the same chip, which means we have more functionality per cost. if the cost of the chip area remains the same, we have more functionality. We have more functionality per same cost. We can do more for the same money. Okay? So this is one motivation, one very big motivation to scale the transistors. But also, if we have smaller transistors, we have faster transistors, which used to translate at least, to higher performance digital circuits. If my circuit can operate faster, I can compute faster, I can do the same task faster. Also, very important nowadays, if we have smaller transistors, we consume less energy per operation. Because the transistor is smaller, the capacitance is smaller, we consume less energy per operation that we're doing using those digital circuits. And this is also very important nowadays because power is very important. So scaling happens. Okay, so what is the result of that? So we have scaling. We can integrate many more transistors on the same chip. We can make our passive devices smaller, put them again on the same chip. So what can we do with that? Okay, so let's see some examples. So what you see here, this is a chip, top view of a chip. This is a collaboration between Qualcomm and the University of California in San Diego. Does anyone know what is Qualcomm? Have you heard about Qualcomm? It's a very big communication company, very, very big. And they own the patent on CDMA. Does anyone heard about CDMA? When you use cell phones, right? CDMA is code division multiple access, which is one of the ways that allows a lot of cell phone users to talk at the same time because they're each given a code. So they can all talk at the same time because every information stream is coded a bit differently, so they're not interfering with each other. Very important for cell phone communication. And this made Qualcomm into a huge, huge company of $1 billion selling every year. Probably your mobile device has a Qualcomm chip. Okay? So this is an example of a CDMA receiver in CMOS technology, integration of this receiver on chip. Okay? Initially, you could not integrate the whole circuit on chip. Once you can integrate this kind of circuit on chip, it enables you to take a cell phone that was kind of a block, if you remember cell phones from the 80s, and make it into something that is much smaller. Another example. Does anyone know what 802.11a means? This is Wi-Fi, one of the standards of Wi-Fi communication. So this chip is actually made by Intel, actually Intel in Israel. Okay, so this is a chip that was designed by the Intel group here in Israel, and this is a transmitter. And one of the important aspects of this specific chip was the ability to integrate the power amplifier on the same chip, which was a huge challenge. What can we see here mostly in the area of the chip? Do you see the transistors? What do you see when you look at the chip area? What is this here behind the words power amplifier? What is underlying underneath? This is an inductor. You see the coil. Okay? You see, even with scaling, it's a huge area out of the area of the chip, which means that this is very important. Okay, so to give you a scale here, then the pitch of these pads, these are the bonding pads of the chip. So the pitch is something maybe 100 micron. Okay? So the chip size is several millimeters, basically. Okay? This is the typical size of those chips. But here you have the power amplifier, and that was the challenge in this case for that project. And you have a lot of other things. You have the mixer that we talked about. We have some amplifiers and all kinds of other circuit that were being used. And again, what do I gain by integrating the power amplifier into the same chip? I make my system smaller. I make my system cheaper. I enable the integration into some mobile device because it's cheaper, it's smaller, so it makes it ready for mobile devices. So if I keep bringing up this iPhone here, it's not the same. This is 4S, but if I ask myself what is inside, let's say, iPhone 5, okay? So you can see here two of the chips. There are many chips inside this phone, but these are two examples. Again, a Qualcomm example, and Qualcomm is really the dominant player in this field of integrated circuits for cell phones, the actual cell communication. So this is a chip that is integrating a transceiver. Transceiver is something that transmits and receives. Okay, so in short, transceiver. And this is what is called quad band. What does it mean, quad band? What? 4 bands, let's say 800 megahertz, 900 megahertz, 1800 and 1900, right? I mean, those frequency ranges about 1 or 2 gigahertz, but different bands for different companies, different countries. You want one chip to handle everything. You don't want to buy a phone that works only in one country. You want to travel with your phone all around the world. So you want one chip to make it cheap that covers all those frequencies, which means I have a transmitter for this band and this band and this band and this band. I have a receiver for this band, for this band, for this band, for this band. And on top of it, I add also GPS, okay? Because I want my GPS. I don't want another chip for the GPS. I can do it at the same chip. Yes?
It says here it's about 0.1 nanometers, right?
No.
No? It's not
No. No. First of all, I'm now talking about this chip. This is the Qualcomm chip. Okay? Okay?
The question, it's more
Yeah.
general.
Yes.
You said Moore's law.
Yes.
Where does it go next? If we're going 1 or 2 scales down?
Oh, well, this is a totally different lecture. This is a totally different lecture. If you're asking what kind of technology these chips are made of, I think both of them are, I think, well, I think 28 nanometer technology, maybe plus minus 1 generation, okay? Maybe 40 most probably 28 nanometer. Currently in production, you have chips at 22 nanometer, and in kind of development also less than that. You're asking where this is going. This is a huge question, and it relates mostly to the digital aspect of those chips. For the RF part, the radio frequency part, you don't care as much because we can have those kind of radio frequency circuits also at older technologies. It's enough for these frequencies. So it's not as important. It's not as important, but for the digital part, it's very important. And it's not a short answer. It's not a short answer. I think CMOS is still going to be here for some years to come, it's a good question of what is going to follow it next, but not the topic of this lecture. Sorry. So what we have here is an integration of. Oh, wow! So we have an integration here of several radios. Here in the example here, we have also integration of several radios, but for Wi-Fi. And this is made by another leader in this industry, which is Broadcom. Also has a strong presence here in Israel. Bought about 10 startups here in Israel in recent years. So this is a chip that handles the Wi-Fi. This is an abbreviation of 802.11n, okay, one of the standards. Bluetooth that probably you're all using, FM radio, all integrated in the same chip. Okay. So in the few minutes that are left, let's see where is the future, at least in my mind, in the research that we're doing here. Okay. So if we go higher in frequency and we want to integrate more things, we can also integrate antennas. This is an example of an RFID chip that we've made at a frequency of 24 gigahertz. Okay, so it has transmit and receive antennas. It harvests energy from the signals that are being transmitted onto that chip. The energy harvesting actually operates the chip. It gives it power. So there is no battery, there is no connection. It's just antennas and the chip, all integrated on the same chip. Still going higher in frequency, 90 gigahertz. We want to transmit very high data rates. Let's say you want to transmit high definition video, uncompressed, 4K resolution. Okay, so this is a transceiver that can transmit and receive 6 gigabits per second. It's actually bidirectional. We can use the same chip to either transmit or receive from the same node. You can see here some signals that were actually being measured of this chip, of those high data rates. In the same area of frequency 100 gigahertz, integrated energy receiver, you can see the antenna. The antenna here on the same chip, it's actually most of the area here in the chip, and this is the receiving circuit. This is an array of such circuits if we want to couple them together. Still going higher in frequency, this is a transmitter, 120 gigahertz. This is the carrier frequency, and it actually has two channels. Usually it's being called I and Q, in phase and in quadrature phase, 90 degrees. So two streams of data, each of them 10 gigabit per second to a total of 20 gigabit per second. So very, very high data rates. And we're using the fact that we can use very high frequencies, that those devices can operate at high frequencies, to use frequency bands that have a lot of bandwidth that we can use to transmit a lot of data. Okay? So this is how the chip looked like. A lot of data, but the area is very small because our devices scale. We need smaller inductors. Still going higher in frequency, this is a receiver around 170 gigahertz. Okay? We actually don't get active amplification at those frequencies, so our mixer that we use for downconversion, it's subharmonic. So we have an oscillator on chip that oscillates at half the frequency, but we use it to, in this kind of multiplication, we multiply our incoming signal with our local oscillator twice, okay, in a way to downconvert. Do you remember the Yagi antenna from before? Okay, so this is kind of a variation of the Yagi antenna, but on chip. Why can we integrate it on chip? Because the frequency is 220 gigahertz. Okay, so it's small enough to be integrated on the chip and to create a transmitter. So we have a source here, the circuit, that is driving an antenna, and this is radiating outside the chip. Still going a bit higher in frequency, this is another receiver at 270 gigahertz. It uses the third harmonic of our local oscillator to be able to downconvert signals at much higher frequencies. Okay? By the way, if you asked before about technologies, then these chips are mainly 65 nanometer technology. We can expect even better performance at future technology nodes. And I think this is the last example. This is a 300 gigahertz radiating transmitter, even going up to 340 gigahertz in one of the cases. And what do you recognize here on the chip? What kind of antenna is there here? Loop antenna. Okay, so this is the loop antenna that we're using. This is the loop. Okay, and it can be very, very small because the frequency is very, very high. Okay. So we're able to integrate antennas, receiving circuits, transmitting circuits, all on the same chip, transmitting and receiving very, very high data rates with a very small chip size that can be made very cheap, okay, for those kind of future applications. So what I was trying to convince you is that communication is experiencing a tremendous change in capability and applications because we can miniaturize our RF circuits and systems. If we miniaturize, we reduce the size, we reduce the power consumption, we reduce the cost of communication, and enable much and much higher data rates. You want to transmit your videos very fast, real time, and this really enables the new applications for the mobile world. And in our university research, we show that the future really holds many more exciting applications that can utilize such high data rates, very, very small size, and we hope that this will really support those future applications. So thank you all for your attention.